The subject I actually want to focus on is a subject called latency. We talk about latency quite a lot, but I'm also going to try and show you how latency can mean different things. And we kind of misuse terms a little bit. And if we want to actually quantify something and put a model behind it, we have to get a little bit more correct. But the really important thing about latency or response time, as we should be talking about it, is when we're dealing with applications, if we get it wrong, bad things happen. And generally, we don't really realize that in a lot of our testing. Often, we don't realize it's happening in production because we don't have good measurement, we don't have good telemetry. And what happens is we have poor customers that are kind of getting this sort of experience. It's not good. Our systems haven't reacted in the right way. We end up with things behaving badly. So a kind of interesting way you can look at this, we all want systems to be resilient, reliable, stand up all of the time. But if your system doesn't respond in a timely fashion, it is effectively unavailable. It's a way of looking at it, because what is the difference between a system that takes too long to respond or never responds? It's pretty much the same experience for any customer. They don't really care. They don't see it. It's a bit like that sort of Einstein quote about if I'm standing in an elevator and someone switches off gravity or the elevator's falling to the ground, can you tell the difference? It doesn't really matter. So response time starts to become an interesting way we need to look at these things. Now, where am I coming from with this? I've worked through a number of things in my career, but the last 10 years particularly, I've done quite a bit in the financial trading space, the gambling space, betting space, games, where all of these things are driven by incredibly high volumes, but the system needs to respond in a timely manner, otherwise we get very unhappy users. You miss the trading opportunity, you miss the bet on the horse race, you miss the game chance that you're actually playing. But also we can be analyzing these and trying to keep up with them in systems that are doing risk profiling, all sorts of interesting things. So if we get this wrong, it's very different from your typical application. So I've probably got a more extreme view of this than most people, but I think a lot of it translates quite well. Particularly when I was at LMAX, as I mentioned this morning, like I went through Betfair and into LMAX. Like we're in Betfair, we were seeing more transactions per day than all the European equity exchanges combined times 2, which is a lot of traffic. But the important thing was we wanted to be really responsive. And during this time when we spun out LMAX, the whole low latency thing really kicked off. Before that, trading was always in the term of sort of like milliseconds, many, many milliseconds. All of a sudden, this raced down into becoming like single-digit milliseconds, hundreds of microseconds, tens of microseconds. Even today, it's crazy. We're now looking at the fastest trading systems where they're talking sub-microsecond. We're talking nanoseconds. You're not writing software in Java to do that. You're writing FPGAs in switches themselves. That's at the extreme. But there's still a lot of interesting things happening further up the stack. Because if you compete in this world, you're one of two things. You're either prey or you're a predator. If you're a predator, you know exactly what you are and you know who you're competing against. If you're prey, so if you're sort of doing normal financial trading, the thing that's important when you're a prey is not to be at the back of the pack. As long as you're somewhere in the middle, you're kind of okay and you're kind of safe. So getting things reasonably good is usually good enough. Just don't be the slowest. The really interesting problem that exists in this space is you're quite often dealing with latency and throughput. People say you choose one over the other. Well, in this world, you don't get a choice. You must be fast, but you also must deal with very high throughput at any given point in time. And the really difficult problem is we get a lot of contention. So we can't just go parallel and throw lots of hardware at the problem, because if you're in the betting space, big events are not scheduled to conflict with each other, like the big horse race, the World Cup football game, the sort of American football games, all these sorts of things, they don't conflict with each other. So all the action is all on the same instrument and things. It's the same in financial trading. It all happens on like euro, dollar, or different things like that. So it's all focused. So we end up having this serious contention problem, and we have to design to deal with this. So if you start doing this a lot, you have to start taking an empirical view. And so where does the time go? Where's the typical time go on an individual transaction? So I'm going to be a little bit flippant here and have a little bit of fun where what really happens with systems that I get to see. So your typical enterprise architecture stack, if you're going to build something, people will usually start off with a way of approaching it. That normally starts off with, let's waste lots of bandwidth doing a lot of REST over HTTP. Then we'll parse lots and lots of XML or JSON. That'll waste a lot of CPU time. We'll probably start experimenting with some new functional programming techniques that are generally quite inappropriate for what people are doing. We'll then wash out all of our caches by allocating an anemic domain model and do all of these data transfer objects that sort of sit around everywhere. We'll generally not think very much about data structures. We'll create lots of keys and hash codes that are really quite poor that turn all of our hash maps into linked lists. Then we'll try and torture some relational database. We'll put an ORM in front of it and we'll have a bit of fun with that. But the ORMs generally will really hurt the database so badly they might kill it, so we'll put a cache in front of that to sort of stop it from dying. And then in the end, we use this perfectly good relational database, but because our application doesn't work very well, we blame it, and then we get some NoSQL in instead. Oh yeah, and by the way, we'll make this really hard by making it concurrent, so no one can understand or how to debug it. And then we'll serialize all of these individual threads on a logging framework that's really slow and inefficient. And the bigger the box we get to throw at this, the slower the whole thing actually gets because it contends on this. That seems to be how our industry goes about building things as a normal way of doing stuff. But it seems kind of insane. Oh yeah, and by the way, we'll scatter a little bit of business logic here and there. Do that important stuff that we're actually paid to do. So if you start looking at what's blocking my threads, what's stopping me making progress, how do I get throughput, how do I get decent latency and this sort of thing, and it's really hard to tell, it's really hard to measure these systems. So let's think about this differently. Let's back up if we consider that was kind of the wrong way to approach this. How about we start with what is the business problem we're trying to solve and just write the business logic for that on its own, nothing else, no pollution. Can we make that go really fast and make it work really well? Usually you can get pretty much any business problem on the planet and get it to run on a single thread and make it work really, really well and really, really fast. And we can understand it, we can unit test it, it's all quite nice. Then we've got to work out how we get requests in and out of that. So we've got to encode and decode. We've got to work out how we receive these things from the network and deal with them. You effectively end up creating a pipeline of just requests coming in and requests going out. Like many of these stages can just be done with single threads. It's all relatively simple. But this is not normally what we see in the world. It's not how we see how things are approached. It means we pipeline things. We are asynchronous. We can put threads into the stages. We can do stuff even parallel inside here, but in controlled and understood ways. And what you start finding is any applications that have got extremes of performance, security, resilience, they all start being designed in very, very similar ways and start looking like some of this. And then you start asking simple questions like, what's blocking any of my threads to making progress? These become easy to answer with this sort of design. So it starts giving you different ways of thinking about it. But all that kind of just leads you into a type of application. What I want to cover today is to sort of take a little step back and look at what causes some of this blocking behavior. How can we go about understanding that? I'm going to cover a little bit about what I mean about latency, a little bit about experiences I've had with locks, what I've learned from them, what I've learned from dealing with queues. But also, I've learned that there's lots of other queues out there in the world. I want to look at some of those and some of the design principles from those and how they behave. We're going to do this all from let's look at how they work, measure them, and see what differences there actually are. And then I want to look at a little bit where we can go next in this sort of field. So, a bit abstract, but let's move forward. So first up, what causes our applications to block? Well, it can come from many different things, but generally we want to access some resource. That resource becomes precious, we end up waiting on it, or we end up waiting between threads for things to happen. Like, what are some of our resources? It can be simple stuff like a network card, a hard disk, some memory, the CPU, the data sets, anything we've got. We need to measure how we access these things and what is the costs and what sort of effects are happening in this. But if we're going to protect access to it, we've got two basic choices here. We've got the good old-fashioned locks, which are a bit like our traffic lights. They work very well. They give pretty good progress. They're not the fastest way to do it, but they're always blocking. So for example, if something is holding a lock and it takes an interrupt, no other thread can make progress. That lock that's holding the thread has locked up that resource and nothing makes progress at that point. Now, generally, those aren't too much of an issue, but it really does stop you going for the more extremes of performance. The other approach is we use sort of lock-free programming techniques that in some cases are blocking, in some cases they're not blocking. The nice thing is they all happen in user space, but they can be difficult to get right and they've got some consequences. Particularly one of the biggest consequences with these is if you have more threads that need to run than you have cores available, you can end up really slowing down your application. We'll kind of come back to that in a little bit. So what I'm going to do is show you some of the implications of locks and then show you some of the other techniques with CAS and what we can do to work around those in different ways. Fundamentally, one of the things I believe in, and I've seen this through measurement being a really useful thing, is if you're dealing with a disk or a network card or some sort of contended resource, don't have lots of things fight to use it, because if they do, you'll spend a lot of time dealing with the complexity, but also dealing with the performance issues of that. If you can have a single writer to any given resource, things get a whole lot less complex. And you can also make them much faster, because we can use batching techniques. We can do all sorts of cool stuff that lowers latency and improves what's going on. So how will we do that? Typically, we end up putting a queue of some description in front of it. And you say, well, I'll put a lock in front of it. I don't want a queue. If you put a lock, you have a queue that you don't even understand, you don't know how to measure. It's really important, and I'll repeat this a number of times, that we need to put telemetry into our systems so we know what's going on. Is how long are our queues? How long am I waiting? You need to know these sorts of things. By putting the right type of queues in, we can manage this. So let's quickly define what do I also mean by latency. Well, one of the ways of looking at it is any given system must have a service level agreement. Now, it doesn't mean that that means it has to respond in 10 microseconds. It has to be what is pragmatic for that system in the real world, but know what it should be. What's good look like, what's not good look like, and sort of agree that and be able to measure it. And you've got to make sure your system makes that deadline. Now, we'll see different ways of looking at that. One of the things we quite often hear is people talking about real time and what does this mean? Well, let's define this slightly different. Let's talk about hard real time. What do we really mean by real time programming? Well, if I was to write the software to control one of these, this is the typical sort of last line of defense you'll get on a battleship. So as missiles are approaching a battleship and everything else fails when it's further out, this is the very last line of defense. On a British warship, this is called the goalkeeper. Very similar to like the last line of defense in a football game is the goalkeeper. This thing has to work out what's coming in, what's going to attack it, and how can it shoot it down at the very, very last second. You really don't want to take a GC pause as that missile's coming in. That would not be good. Sorry, going to save point now. We'll work this out later. So this is very different. And the important point is when you say something is a proper real-time system, hard real-time, that means that if you do not meet your SLA, it is a catastrophic failure. If the software does not respond fast enough with one of these, it's a catastrophic failure because people die. So that's what we mean by hard real-time. What's kind of softer real-time? We hear this a lot. I kind of think, well, this is to me is finance. If our software doesn't respond in a timely enough manner, we don't have everybody die. But we have people lose a lot of money, maybe. So it becomes important, but it's not a complete catastrophic failure. In fact, even sometimes you'll probably get away with it. But if you end up being late too often, you become vulnerable, you're at the back of the herd, you get picked off. So kind of soft real time like that. I kind of like to always use the term squidgy real time for real systems. And this is where real users just get fed up waiting on our systems. Given how fast modern hardware is, there is no excuse these days why a website takes a long time to respond. Like, if we can do financial transactions in a few microseconds, we can surely order a book online in like a lot less than a few seconds, what it seems to take on many given sites. So we've got to get this stuff working well. The fun usually comes in when we're talking about, well, how fast are we? Is it the average? Is it most of the time? But most of the time is the kind of interesting problem, because generally people are unaware of how bad it does get. So One of the things I loved about working at Betfair that was defined early on was the concept of the bad bet. Any business transaction that took more than 1 second had to be investigated. We found out why, and that caused us to improve the system so much. So that was the end user stuff. It was the automated stuff we wanted it to be even faster. Because I quite often find people are in this sort of thing, is they're kind of happily digging along, it's all kind of great, and they have no idea what they're going to let themselves in for. Quite often, people, when they put telemetry into the system for the first time, really would like it switched off again. They don't like to see the world that's just been exposed to them. They kind of like their kind of happy world where they believed it was great before. And what I find, why we end up with these bad pauses, why is it bad? It's always about the blocking. So something's blocking something else making progress. We've got to find out what that is and how to fix it. So why do I end up thinking a lot about blocking and queues? Well, I spend a lot of time doing this, and this sort of really illustrates queuing theory to me really well. It's like, what is response time? What is latency? What is service time? These sort of things. This is where it comes from, a thing called queuing theory. So this is work that goes back over 100 years by Erlang. And what he discovered from the Stockholm telephone exchanges, sometimes it was taking too long to get a phone call connected. But what was going on? Well, what he discovered was there's the service time itself that needs to be dealt with, and that's like the phone call. That's going to hold up the resources for a certain period of time, and we can do so many of those. We also find you spend a lot of time waiting. That's the latent time. That's actually what latency is, the time you are latent waiting for something to happen. And the overall time for things is the response time. So it'd be kind of nice if, as an industry, we actually got a bit better with our terminology and use some of it right, but we are where we are. What I also find quite interesting is the time to enqueue and dequeue is often one of the biggest factors that we need to think about, and we need to factor this into what we're doing. Now, we'll all probably have seen this classic J-curve, where you load up a system, and then after a while it becomes quite unresponsive. It follows this curve. And what's happening here is the more you utilize any given resource, the more the probability that it's going to be in use if you turn up to use it. So basic probability theory, like if you're using something half of its full time that's available and you have another transaction turn up, you have a 50% chance you're going to have to wait for the thing that's using it before to finish before you go to use it afterwards. It's like if we go for the door, if we all go for it at the same time, there's only like 1 second can get through that door. We will all end up waiting for a few hundred seconds to try and get out that door because we will queue. Yet if we all just go at nice, regular paces, you'll find that we won't queue, we won't get such a problem. So systems end up having this interesting effect. Now, where does this curve come from? If you're kind of interested in the math, look up a thing called Kendall theory. That particular graph was an MD1, and this is the formula for it, where we can work out what is the mean response time, and it will always be a function of utilization and service time. So knowing how long it takes you to deal with any request is really important for factoring into your models. So one of the things I love to do is put a histogram in front of all of my services and measure the time they take. You capture that, that's a really useful piece of information, because when you actually look at what utilization is, it's arrival rate times service time. So service time is one of your key measures. So that's something, build it into your system, get the metrics right, capture how long it takes you to process any given request to use something. And how do we improve our systems? So one of the really simple things we can do is, if you can batch up the use of any expensive resource, you greatly reduce the utilization and therefore greatly increase the response time, making it much better. You also get much better throughput. So batching is not something that actually makes latency worse. If done correctly, can make latency much better. So let's move on now. We'll set the scene. We've realized that we've got these expensive resources. If we've got to put queues in front of them, or if we've got all the stages in our pipeline, queues are kind of everywhere. Let's look at what options we've got and look at where the costs are kind of in there. So one of the things, if you do a lot of measurement here, you start realizing quite quickly that some queue implementations, you spend more time in queuing and dequeuing than you actually spend in queue time, which is not how most people normally look at queuing theory. So it's the implementation of the queues is actually causing more of the problem than even the queuing theory itself. And this is down to what is fundamentally the evils of blocking again. So where does this come from? Well, if we're going to use plain Java and we're going to use the put and take methods of a queue, those are blocking methods. You go to put to a queue, you will block if the queue's full until there's available space. You also block if something else contends with you based on most of the implementations. They typically have locks. The producers tell the consumers that something's available by using condition variables, and vice versa. The consumers can tell the producers that stuff has been removed by condition variables. That fundamental part of it, if you measure them a lot, is where all the time goes. And it's a really interesting profile. So if we look into how do I use a condition variable to let one thread know that another thread has something ready for it, we end up using these. And so here's a simple example. I want to take a histogram and I want to measure the time it takes for one thread to let another thread know that something's ready via a condition variable, and it echoes back that it acknowledged that. So it's a round trip, a two-way. And I'm going to record this all into a histogram to see how long this actually takes. Well, this is what I end up finding, that my 90th percentile is around about 8 microseconds on a well-tuned Linux box. Now, I emphasize a well-tuned. This is not virtualized. This is bare metal, really stripped down, the sort of thing you would use for financial trading. And as we go further up, we start finding a number of the requests can take a lot longer than even the 8 microseconds round trip. The worst case on this one, when I measured it last week just, was over 5.5 milliseconds, just to signal across condition variables. Now, here's an interesting fact. Does anyone think that this is faster or slower than sending a message across a network? Hands up for who thinks you can send a message between two machines less than 8 milliseconds. Cool, so we've got a few people who are aware. That is correct. On the best network stacks that we have today with the better networks, we can do exchanges between machines faster than we can signal now across threads. That is kind of mind-bending in some ways. So it sort of puts an interesting context on stuff. But that's actually the bad news. Because what's happening here is that was a micro benchmark where the cache is hot, it's not doing anything else, and it's doing this in a tight loop in a micro benchmark. If you measure using condition variables in a real-world application, you're going to see a mean more like 50 microseconds and going significantly higher on the long tail when you've got an application that's doing lots of other things and the cache is all getting polluted as part of what's going on. So these things are incredibly expensive. So what else can we do? Well, let's not look at put and take. Are there other APIs? Well, there are. There's better APIs than that in Java. And we can use offer and poll. And what happens is they don't entangle the producers with the consumers now. So you don't block. You offer to a queue. If the queue's full, it returns false. You can try it again later. You can also go off and do other work. Poll is the opposite side for the consumer, where I can poll out of a queue. If there's something there, I get it. If not, I get null, and I can go off and do something else, or I can try again. This can make quite a difference. So rather than dealing in microseconds before, so the next set of figures I'm just going to give you are in nanoseconds. So we're going to step down. For reference, all of the code that I'm going to talk about here in benchmarks is available there. I'll give you another link at the end. I've done this all on Java 8, update 60, running on an i7 processor that's quad-core, and using a recently patched version of Ubuntu. So fairly nice, reasonable, recent machine. These are sort of figures that you end up getting. It's Ivy Bridge, it's not Haswell. Some of the stuff gets much faster again with Haswell, which is a later processor. So I want to look at a couple of scenarios. So one is whereby I want to send a message from one thread to another thread and get an echo back. So response time. So I'm going to send a burst of one message and get a response back. I'm also going to do a burst of send 100 messages and get a response back to say all 100 have been delivered. Not 100 responses, just I'll do a burst of one message and then I'll do a burst of 100 messages. I'm going to time how long that actually ends up taking. Well, Here's the figures for what you get with the JDK. Now, as a baseline, I've put in wait-free queue that uses a couple of concepts. One of them is the Lamport concepts, another one's fast flow concepts. You don't need to worry about what they mean, but what you can take from it is those are some of the lowest latency queues I've seen, and I've been researching this area for over a decade. So our baseline says you can do that in 167 nanoseconds for that, with the 99 percentile running at 189. So that's really very good. It's a nice place. So let's compare that to an array blocking queue, a link blocking queue, and a concurrent link queue. And looking at these figures, array blocking queue and link blocking queue, yeah, link blocking queue is a bit better than array blocking queue, but concurrent link queue is so much better. It's just like a world apart from those other two. So if you need to exchange fast between two threads in the same process, concurrent link queue looks like a really good candidate for what you want to deal with. Like, I just would not even touch a array blocking queue, and it's going to become even more interesting in a second. So that's a simple one-to-one. You will get a bit of contention, but not a lot of contention. Notice I'm also comparing 1, 2, and 3 producers. So in the one producer case, there is no contention between producers, and it gets echoed back straight away. So the only contention I'm dealing with is producer and consumer on the same data structure. And what you see here standing out is array blocking queue has more contention than link blocking queue, because link blocking queue uses separate lock for the head and a separate lock for the tail, where array blocking queue uses the one lock for both. Concurrent link queue doesn't use locks at all. It uses lock-free techniques and has no entanglement between the producers and consumers, and so it performs much, much better. It's a kind of very nice implementation if you need multi-producers, multi-consumers in a queue. Now let's look at it with a burst length of 100, which is very different at this stage. So in our 100 burst length, I'm sending those 100 messages and then getting a response back. Now, if I start looking at this, array blocking queue and link blocking queue are really not looking very good at all. In fact, they're looking way worse now than concurrent link queue, which looks fairly respectable. So we're getting to the stage where, like, that's 180 microseconds. That's multiple trips between two machines to use array blocking queue to hand off messages between two threads. So this is not a good place to be. Concurrent link queue, still looking strong. It's looking very strong in this sort of scenario as a good way of doing things. And so it's great on the mean, and the 99 percentile doesn't get much worse. I'm not giving figures like sort of 3 nines, 4 nines, 5 nines are maximum on this, because what you tend to find is those are systemic effects that are causing a lot of that. And it's a really interesting area, and you could do a whole talk on the systemic effects on its own. For example, GC going on in the background will cause much larger pauses than we're seeing here, and then that skews a lot of the results. It's important stuff, but I want to focus on the algorithms itself for this. So concurrent link queue looking really good at this stage. Now we've got to answer a couple of really interesting questions about real-world design and real-world applications, like I want backpressure. Any system that cannot provide backpressure cannot meet a response time guarantee, because if you keep accepting new requests in, the queue grows unbounded, and an unbounded queue, if you apply Little's law to it, will end up with a really bad response time. Back to the basic queuing theory, but it's actually worse than that. Unbounded queues, from I've seen in almost any system I've dealt with, ends up with some point where the producer outpaces the consumer. As a result, the memory grows really big. Once it grows bigger than the L3 cache, you get into this really bad scenario where the producers are cache hitting and they can go faster, the consumers are cache missing and they're going even slower again. At that stage, you get a runaway feedback cycle and you get an out-of-memory error. That's not a good place to be for meeting a response time guarantee. You need to be dealing with it better than that. So it also says we've got to measure a system. So part of measuring a system is knowing the size of a queue. Now, if you call size method on array blocking queue, it takes a lockout. That stops the producers and consumers exchanging between each other under the lock. This is not good. A telemetry system should not perturb the system it's testing. It should, at the best case, cause a very, very small impact, not a huge impact, like actually cause a lock and cause a blocking operation. Link The link blocking queue, similar problem. Takes a lock out on the whole thing. Causes the problems to get entangled together. Well, concurrent link queue was their kind of nice category from before. It doesn't use locks, but it's a linked list and it's not a constant time operation. To get the size, it has to walk the entire list to count the number of nodes that are in there. So there's 3 cases where we do not get the ability to have telemetry on our queues. This is kind of fundamental. Queues that cannot be read by another thread in a concurrent context have got some serious usability issues if you're going to build a system with telemetry and monitoring. If you've got really, really low flow rates, you're only sort of dealing with a few hundred transactions a second, that doesn't matter. When you start dealing in the high rates, it does matter. We also got to be able to measure our flow rates, like how many items have gone through a queue per second, per minute, per hour. These sort of things should be built in as first-class concepts to a queue. Other things we need to consider is, like, if you're dealing with serious performance, we don't want to generate garbage, or we want to generate a minimal amount of garbage. And unfortunately, the queues that we get with this, the types of locks that they use end up creating linked list queues on those locks themselves, so that generates garbage. Things like the concurrent link queue, with it being a link queue, generates garbage too, because it's got nodes in it. So using these in a low latency environment, unless you've got a really good collector like Zing, is not pragmatic either. So we're kind of stuck here, is that concurrent link queue looks good, but it doesn't meet the real world requirements that we need for these sort of systems. And also, between our stages, we sometimes need to fan out. So we need to sort of like take a message and send it to multiple consumers at the same time. We want to do that efficiently so we don't have to create more garbage, have the whole overhead of in-queuing over again multiple times. So there's all these real-world requirements. What do we do about them? Well, let's look at what the alternatives are. So there's a number of inter-thread and also inter-process FIFOs, or FIFOs first in, first out style structures. One that I got involved with was the Disruptor. So Disruptor 1, Disruptor 2 was something I was heavily involved with. I kind of led the open source effort on that. And we built a ring buffer that was using techniques that didn't use locks. So we were using CAS operations on a number of things. So the basic algorithm for this was, if you wanted to exchange between producer and consumer, the producers ended up performing a CAS operation. So it's a compare and set atomic operation on what was known as the cursor, this thing here. That let you claim your turn. This is a bit like the deli counter ticket idea. This comes from Lamport's originally bakery algorithm as a concept. You claim your turn, you then take your turn. Once you take your turn, you use the slot that you have in the array. It's just a circular buffer, so you take the sequence, you do a modulus arithmetic on the sequence, you use that slot. So that means you can, with the Disruptor, you didn't need to put an object in because you could pre-allocate the objects. You could then just mutate it without having contention, set all the fields that you wanted, and then you said it was done by updating the available counter to be the same value that the cursor had got to. Now when we've done that, the consumer knows what they can consume. We added another counter, which was that concept of a gating concept. That meant that the producers don't overrun the consumers, and that provides the back pressure. It's actually a relatively simple algorithm at its core. It kind of had an interesting thing in it. So here's one of my big confessions of my concurrent programming. So one of the other guys I was working with in the team, he suggested this, which was kind of interesting. He didn't come from the concurrency background that I did, and I thought this was a beautifully elegant idea, and I let it go right through to production, and we built systems based upon this and how we tested. And so this simple algorithm works like this. So whenever I go to say that I'm done, what I have to do is I've got to set the cursor up to the claim sequence. Now, how do I know where all the other threads are so the consumer gets it right? Well, the premise of this algorithm is quite simple. If the cursor has currently reached the position just before where I am, I know everything else is complete and I just bump it ahead. It's beautifully elegant, really simple. In fact, it actually works really, really well whenever you've got more cores available than you've threads that need to run, because you don't get any starvation problems. Now, the fun comes in is, what if I have less cores than I have threads, and I end up having an interrupt, so two threads going through exactly the same process, and I take an interrupt on one of the threads between those two lines. If I end up doing that, the other thread is just spinning, wasting a CPU, waiting for the one to catch up, and it cannot make progress. So we have a blocking operation. So this has nothing to do with locks. We can have blocking operations between threads just because the algorithms get entangled. How do we address that? Well, rather than having a single availability counter, we had a counter per slot, and the slot sequence just said where it had got up to for a given circuit around the ring. So we basically use memory to compensate for the algorithm. Simple approach. So the Disruptor 2 to the Disruptor 3 was just a move forward of adding in this availability array. It was a slightly more complicated algorithm, but what did it do to real-world performance? So I can give you figures, but here's a real example a client has let me share, where it's a financial trading company, and one change we made was moving them from the Disruptor 2 to the Disruptor 3, and what did it do to the behavior of their actual system? Well, this was the Disruptor 2. This is an example of running through a few billion transactions through their system and plotting every single point of every single transaction. I actually love these because they tell you so much that figures don't tell you. And this is what the system was running like at this point. The scale is kind of small on the left, but basically that line is coming in at 80 microseconds. It's a log scale. So this is a financial trading system, needs to go quite fast. We're looking at around 80 microseconds for this with the Disruptor 2. We added in the Disruptor 3, and it dropped down to there. So this is not the thing, this is the whole system end to end, and this is used in a number of places. We dropped from 80 microseconds down to 50 microseconds. That's a major improvement in throughput. But what was also, and the response time, what was interesting is other effects become more visible, more pronounced, so we're able to go and investigate what those other things were. So, like, between two algorithms, that's real-world experience of how systems change. And so you think you're dealing with tiny little things, but it can actually make quite a big difference to a real-world application. So that's the disruptor. That's one way of doing it. But you may say, well, what if I just need a queue? I can't change my existing code. I want to just put a queue implementation in instead of one of the ones that comes in JDK. Well, one of the better ones I know from looking at this is a combination of taking some of the Lamport queue concepts. So Lamport wrote a number of papers in the 1970s where he put some ideas on circular buffers and queues, where he introduced this concept of a head and a tail. And the idea is use the head and tail counters to work out where the producers and consumer is. His queues were based on single producer, single consumer. We can evolve that to be multiple producer, single consumer by doing the CAS operation on the tail. So we do a compare and set. So we check if we've got space. We've read the value of the tail beforehand. We'll move the tail forward by one, conditional on that no one else has moved the tail. So nice CAS operation lets us move that forward. How does the consumer work? Well, the consumer doesn't actually read the tail. The consumer just knows the last place that it read. It reads one slot forward in the array, and it just reads the array itself. It needs to do a volatile operation on the array. What's kind of difficult doing some of this stuff in Java is we don't have the support in our memory model as it stands to do volatile reads on an array. So you have to do some things with unsafe to make this work well. So this one was implemented using unsafe. It's combined the fast flow for the consumer, the Lamport for the producer, and we exchange with these counters, writing references into the array. It's a bit simpler than the disruptor because you don't need the array of availability counters. We just use the array itself as the means of doing that. So it's a nice, elegant refinement on that. Now let's look at what the figures look like for this. So again, burst length of just 1 to begin with. How does this look? Well, our baseline, again, like that 160, we've got our concurrent link queue. It's looking good. It's a bit better than the concurrent link queue, which is a kind of baseline we're going to compete with, but not massively better. It's kind of getting on for almost a factor of 2 at the sort of 99%, so that's kind of good. But the nice thing is we meet a lot of our other requirements. These structures can tell you the size of the queue without it being a blocking operation. They can also tell you flow rates. They can do other interesting things that we need. So we're kind of matching what concurrently in queue can do, beating it a little bit on performance, but meeting much more requirements. So that's kind of interesting. Now let's go forward and look at, well, what happens if I really ramp the contention? I hit it with bursts of 100, so all the threads are going to now contend much more. And what starts to happen here is in the low contention, it looks good for these queues. Things are all working really well. But there's what's happened here? There's an interesting effect that happens on high contention where basically it all equalizes. All things kind of become about equal whenever a contention gets high. And that is fundamentally because at the heart of all of these algorithms, there's this blocking operation where you read a value, you then make your choices of what you do next, and then you cas in the results based upon that. And what happens is those spin loops end up having a blocking effect on each other because you'll end up reading something, it's moved, you need to read it again, and as you increase contention, these problems repeat over and over again. And so they all sort of converge under high contention to have roughly the same problems. So let's look forward. Can we do better than that? Can we move forward? You may also notice, if you know the disruptor, but I'll give an example of one producer, and I've given an example of batching, that the disruptor has ways of doing those in a better way. Yes, it does, and it can get better figures than this, but I want to compare the like for like with genuine multi-producer cases rather than just specialize it and make it look good. So what else have we got? So quite often we're also trying to exchange not just between threads, but also between processes. As we're getting these large multi-socket, multi-core boxes, we have to hand off even between processes. In fact, it's good to have one node doing I/O that's connected to the network card and another node doing a lot of compute and memory-intensive stuff, and keep them apart. Because actually keeping our L3 caches apart has become a really important thing to overall performance. So we want to sort of separate our processes out, but let them communicate, but not let's communicate via the local network stack, because that's not that fast. So let's sort of put together a simple hypothesis and way of thinking about this. And if you imagine, well, what would be a real-world use case for this? So imagine a logger. What would the ideal logger look like? So one of the classic problems we have with logging is it all contends, all those threads contend on the logger at any given point in time. So if I get more and more threads, it's going to cause that contention problem to happen in there. Also, the really, really important problem with a logger is if you have a process crash, usually the last few things that you've written are the most pertinent to knowing what could not have caused that thing, but you've lost it because it's in a buffer that's part of your process waiting to be written to disk. That's pretty much how all loggers work. Now, how about if the logger run out of process and you sent it a message? Actually, logging is a messaging problem. That's why people look at it the wrong way. It's fundamentally a messaging problem. You want to send a message to an archiver and deal with it. So I want to ensure that the last few messages before a crash have safely been dealt with. So it needs to be written out of process. So start thinking about, when you think in process, out of process, there's good reasons for why we want to go out of process at times, even down to simple things like loggers. So one structure I've built that is often used for logging style scenarios is a many-to-one ring buffer. Why many-to-one? Because you want to be logging down to disk just off one thread and batching it and making it all clean, but you've got many, many producers that will end up generating the log events. How does this typically type of thing work? Well, we have a memory map file. We write into it using a head. So write in using the tail. We consume out using a head, and we move forward the tail using a cas operation. Very similar to what you've seen before. Very influenced by Lamport style designs and how they work. And you add in a new message just by moving forward the tail, put in the message, put in a header on the message afterwards. You take out things by copying it out by the consumer, moving forward the head so that way I've got back pressure and know that I don't wrap, I don't have a problem with the producers overrunning the consumers. And with this being a memory map file, it's out of process. If your process crashes, the consumer can continue on writing it and archiving it if you don't have a complete system crash. So it's a kind of nice way to do this, and it tends to work very well. What's in a header, just kind of for reference? Well, you only really need two fields for this. You need to know the length of the frame that you're going to deal with and the message type itself. So everything needs an ID so we know what we're going to be parsing. And then we've got the encoded message that comes after that. And the order in which these are written becomes important. If you write the frame length last, by writing the frame length last, you know you're done. And the consumer can just go by reading ahead through the buffer. Because it reads a message, it reads its length, it reads the next one. If the next one is 0, it's already reached the end. It doesn't need to do anything more complicated. It makes the consumer incredibly quick. But when you start measuring this in a real-world problem, you find out that the consumer has to zero the file to make it reusable. So it can give you really good latency, but its throughput ends up being hampered by constantly not just reading out, going and zeroing out that file for reuse again afterwards. And that will seriously cut down the throughput. So we need to work out, how do we deal with this and yet get some of the benefits? So I've been working on a messaging system that was working between different machines, and our goal was to make something that's faster than anything else that's out there with lower and more predictable latency. It's a kind of interesting challenge. It's kind of a fun thing to do because one of the people I'm working on it with is Todd Montgomery, and if there's anybody here has used LBM from 29 West, that's what Todd did last before he came on to do this, and he's worked on a number of other messaging systems and multicast stuff, and he also has done communications software that's even gone up into space with NASA. So this guy knows a lot about these sorts of things, so it's been a joy to work with him. But we were trying to work on data structures and network protocols that could address this. But one of the things we also had to address was, how do we hand off between the threads within the messaging system itself? And to do that, we need an IPC mechanism that works, but how do we break this contention problems? Because we realize we're getting more and more cores all of the time. How do we address it? And one of the fundamental things we had to address was breaking that CAS spin loop. If we have that at the core for design, we will not better anything else. We've seen how that fundamentally limits every other implementation that's out there. So we were trying to come up with a new design to deal with that. We also had some other concerns in that when you're sending data onto a network, you get loss. So you need to be able to retransmit. So the data structures must be persistent from a functional sense in that it'd be great to be able to reread them any number of times. They're idempotent to read and be able to resend the data over and over again. So with all these really great requirements, and drove us to a quite interesting implementation. So taking this sort of similar concepts from the ring buffer, we looked at how do we do it better. Well, let's go ahead, just write messages in the same sort of way that we do with a ring buffer, just breaking down what are the steps. So move forward the tail, copy in the message, put the header on the message. It's also important to put the header on the message for the full network packet if you want to ship this out on the network to be really fast. And so that's really quite simple. What does the header look like, just for reference? Because when you compare the figures for this to the other things, you've also got to consider that this is putting a full header that can go onto the network, onto the message. For anybody who's interested, that's ITEF protocol porn. A lot of people end up sort of looking at these things having their normal day. So we had all of these fields, but we also fundamentally have the length field the same way as the other protocol we've seen before. The cool thing about this is it's append-only, and append-only structures can be read by any number of consumers without locks. So this actually solves the fan-out problem really well, as we can have many consumers of this as well at no additional cost. So how would you do this? Well, if I just keep doing it, you'll end up with one big file that kind of goes on forever, and I've seen people attempt this before, but if you do it and you measure it, you start discovering there's some fundamental issues. It's not the right way to do it. You find that you get page faults all the time. You really pressure the VM system in Linux. In fact, you can pressure the VM system in Linux so much that you can't get in on a console as root to even do something about it. It won't respond for quite a few seconds at times as it's dealing with this sort of VM pressure. It's not a good thing to do to the operating system. So what can we do in turn? Well, take an inspiration from backpacking. If anybody's ever backpacked a long distance for a long time, you get round to the wash one, wear one, dry one. That's all you need. You keep things really, really simple. And we do the same thing with the logs. We have the concept of the current active log that we're adding to. We've got the one previous that's dirty and will be idempotent that can be reused again for resending messages, for doing anything else that we want. And we've got a clean one ready to be used next. And we just cycle around those. So we become effectively persistent for a reasonable period of time. And we track where all the consumers are, and that way we can apply the right sort of back pressure. But what about that zeroing problem? What about tracking all of that? Well, what we do is we use another thread. We have all of these cores now. So if we use another thread to do the zeroing of the file in the background, doing the upkeep of all the counters for back pressure, we've no longer got the entanglement between producer and consumer, even for the housekeeping, never mind that. So let's get back to that question of publishers. How do we make sure they don't block each other? Well, if I've got two threads racing with each other to put messages into the log, what they need to do is they each will update the tail, but rather than do it with the cas now, there's a really nice x86 instruction called lockxadd. This is available now to us in Java 8, which is a really nice step forward. So Java 8 gives us an opportunity to build algorithms like this that we had to previously build in C. So now what I can do is one thread can do a lockxadd. There's no spin, there's no retry. It just moves forward the counter for a given amount of space that it needs and gives me the value that it was before. So I know I've got from that position for the amount of space that I want. Now I can freely copy data in here with no entanglement between the producers. The other thread is doing a similar thing. It's done a lockxadd, but it's hit a special case. So the first one copies in its message. It all fitted nicely in the log. What happens to the second one? The second one that went beyond the end. And if you had any number of threads, the same thing works here. You agree a protocol of interaction, and the thread that caused the log to go beyond the end, another one could have happened to move the tail further down. But only one thread moved it from before the end of the log past the end of the log, and that's a simple calculation to work out which thread done that. The thread that done that puts in a padding record and is responsible for rotating to the next log. So this wash one, wear one, dry one, that's just a rotation. And all the rotation involves at that stage is writing up a couple of integers to say which logs we're now currently using. So it's a really fast operation for the rotation of the log. It's already been all zeroed and prepped in the background by another thread. And at that stage, you just copy in the message to the next log. So we've done all of that without the threads blocking each other. They're able to do that without the spinning cas loop. So that was our theory. This should work. This should be a better way of dealing with a highly contended log with multiple producers. But it's a theory. We've got to measure it. We've got to see, has it actually worked? So let's look at it with, first of all, our burst of one, like we did before. How does things look? Now notice we're dealing with really quite small numbers now compared to the many microseconds before. So our baseline is pretty good. If we compare to concurrent link queue, we're getting significantly better, and particularly they're starting to get a lot more consistent at the 99%. So our on IPC is the new interesting algorithm as a way to approach it. It's a kind of interesting way of looking at this world. Now that's the one producer, one burst of one message echoed back again. So that doesn't cause a lot of serious contention. They contend sometimes, but not an awful lot. So let's give it a burst of 100 repeatedly so they're constantly contending with each other and see, do we get into that bad case scenario? So what happens when we do that? Figures are looking really very different now from before. Particularly, let's look down here. Two producers or three producers contending with each other with large bursts. For the first time, we've broken the link seriously with things like concurrent link queue and other things that do the spinning cas loops. We ended up having the ability to really get through under contention much, much more load. And this is just a fundamentally simple change in the algorithm means that we can push latency figures that just no other messaging system is doing. And this is IPC as well. So between two processes, we're looking at exchanging 100 messages in this sort of time. This really matters compared to, remember back when we looked at the array blocking queue, that was 180 microseconds, 180,000 nanoseconds in comparison as a way of doing stuff. So just changes in algorithms, changes in approach, and the cool changes that we now have in Java 8 that we can get to these things and use them. So that's where we are. Where can we go? So part of building this, Todd and I have been having a bit of fun with each other. We kind of have settled into a world where we both can write C++ and Java, but we've kind of agreed to, Todd will work on the C++ implementation, I'll work on the Java implementation, and we'll compete with each other, and we'll try and have a bit of fun. And it's been really frustrating me because what's generally happened is the C++ has been a good bit faster than Java for a lot of it. And every time I get an algorithm improvement that beats the C++ stuff, Todd can just copy the algorithm in C++ and beat the Java implementation. But the reason the C++ is better is for a couple of very simple points, which we could address in Java. Now, what are these points? So if we're going to win the C++ versus Java shootout, one of the first things that the C++ has a big advantage is when we've got these busy spin loops, x86 has an instruction called pause. And this pause instruction does two things. One is it prevents speculative execution. So our processors are known as speculative out-of-order execution engines, and they go really fast. So when they hit a branch or they hit a loop, they can go further past it with guesses on how things are going to happen even when they've had cache misses. We don't want that to happen whenever we've got spin loops between threads because their guesses are usually always wrong, and they have to unwind that state, which slows them down. Also, when they're doing that, they're wasting a lot of energy and they're not letting another thread run on the core, so this prevents throughput. Now, we could easily add this sort of thing to Java, and there's a JIP proposed to do this, where we can add a hint to a thread or some other class, and that would put as an intrinsic into the code something to do this. Prototypes of this are showing things like in the Disruptor, improving 20% on latency. It makes a big difference to having this stuff across all nines. It's a nice way of working. Another one of the problems that I keep getting frustrated with is what we call data-dependent loads. Java is an object-oriented language. We have objects that point from one object to another object to another object, and that makes a nice model at times. But each time you follow one of those pointers, you can potentially get a cache miss. And our processor cannot speculate and go ahead to get that stuff. And as a result, it slows down a lot. Where in the C code, I can express the way I want to lay that out. Like, this object always comes with this and this and this, and it's always together. It's in the same area of memory. And if I have a pointer to that, I know from the pointer I can get to the other thing by just mathematics. I don't need to chase another pointer and chase another pointer. The object layout proposal that Gil, Tene, and I have put forward addresses a lot of this. We can do a lot of these things. And I think of many of the serious performance problems I see where you do an in-memory compute, it's about 70% of the case that's memory related. About 30% of the cases could be improved if we had value objects. Now, value objects would be a great thing, but applying Pareto's principle, which one should we be doing first? I would argue, based on what I'm seeing from the field, that actually object layout has higher value. We could build better data structures now in the JVM, and in fact, we can do it without a language change. I found another interesting bug as well. So when I'm copying memory from one buffer to another buffer, I was discovering that C could be running at 45, 50 gigabytes a second. Really nice. And then I run the same Java algorithm, and I always expected to be a bit less, but not a lot less. It was showing up at 2.5 gigabytes a second, like 45 to 2.5. What's going on here? Kind of been investigating it a little bit and discovering that Java, if you're dealing with copies and they're not aligned on 16-byte boundaries in some cases, are a lot slower than when they are aligned on 16-byte boundaries. Like, a good way to trick some of this is if you turn on the G1 garbage collector and you deal with large arrays, things get aligned to these boundaries, and you can see that it's a lot faster than when it's not. So we obviously have some areas for performance improvement inside our VMs that can sort of help and deal with this. And I know some guys who've been experimenting with this inside the JVM to make it faster, because this would be a really useful thing. It's just a good fix that we should have. And kind of last but not least is the queue interface itself. There's a fundamental design mistake has been made here. The queue interface has been taken across from Java collections. I think we fundamentally should not have just made all of our current collections extend the normal collections classes that we had before, because there's a conflation of concern in both offer and poll. And offer and poll conflate the concerns of, is there something available now, and am I full or am I empty? Now that may seem like no big deal, but it makes a massive difference to implementations. So for example, many concurrent algorithms can have a point where one thread takes an interrupt and another thread makes progress. So you can actually have 5 or 6 things put into a queue, but one thing further back hasn't completed. Now, if you happen to read at that stage, nothing is available. You can't get to the later ones until the earlier ones complete. So poll could return null at that stage. But if you implement the contract correctly, you can't do that. You have to busy spin inside the implementation waiting for it to happen. As a result, you end up wasting CPU. You can cause the system to get into really bad blocking effects, and it gets quite nasty. It should be a case of each method should have a single responsibility and not have conflated concerns, and we wouldn't get into that sort of issue. So there's some interesting things that are in there. Also, I've heard from a lot of people who worked on the JDK that one of the really annoying things in the concurrent stuff is like implementing iterators with remove on an iterator, for example. That becomes a hugely complex thing in concurrent collections, which generally nobody actually uses in real life. So maybe there should be different implementations and different ways of doing stuff. So, kind of quickly coming to wrap up, one thing to think about. Just this week, Amazon announced they're going to be releasing the X1 instances. These are going to be 2 terabytes of RAM and over 100 vCores. We're going to have massive numbers of threads with a lot going on inside our VMs. If we can't come up with better ways of dealing with concurrency on this and splitting things apart, we're not going to benefit from them. So we've got to think about this. There's great opportunities going forward. These will be available early next year. And kind of where can we find all of this? The collections that are all up there are in Agrona. Aaron's up there, and there's benchmarks. So you can go and test this for yourself, see what figures you get. On that, I'll wrap up, and I think we're just about out of time. So thank you all very much. I don't know if there's time for questions.